Welcome to the Marathi ML channel. Today we are going to see how to fine tune the LLM model using the QLORA. I will explain you in a minute what are the things we are going to use. But first of all, I want to thanks to one of a user who commented in my previous video and asked us to do the video on data preprocessing of unique data set and then fine tune using the LoRa method. However, in the same video, I explain how to fine tune your own data using the LoRa model. So in this video, I am specifically focusing on how to do the data pre-processing because when we are doing the fine tuning, it is very important you to do the pre-processing of your own data set. You cannot feed directly to the LLM and then LLM. We have to do some little bit pre-processing so that LLM can understand the data and then you can use that data for the fine tuning purpose. However, last time in this video, I already explained the LoRa. There is a single line of code is available using that you can do the LoRa fine tuning. If you think you wanted to watch, please, I would request, please go and watch this video before before watching this. But there is no as such interlink between this video and that video. You can watch this first and then you go and watch that. It will be definitely value addition. The value addition in such a way that in this video I'm using the Microsoft PHI model, PHI-2 model for this. So here you will get one more value addition that you will come to know how to fine tune the model how to fine tune the PHI model using our own data. And for the JEMA model, I would suggest watch that video. Again, in my last video, I have explained how to evaluate the RAG system. So this is very important when you are feel that I want to implement the RAG but don't know how to evaluate the RAG. Then I'll recommend you go and watch this how to evaluate the RAG system. Let me as you can see in the screen, this is the video for how to evaluate the RAG, and in my, this is the video about the JEMA model. So I would recommend please go watch this video and it will be very value addition. If you feel there is anything needs to be added, anything to be improvised, please feel free to comment on the comment section. It will be very motivating for me to make such a video. Okay, let's not waste much more time and let's jump to this video. Okay, so I think everyone knows that what is the fine tuning, but if someone if someone hearing this first time this term of fine tuning, so let me explain in again in very simple word. We know that generally there are the sorry, just go to the first slide, third slide. Turn on pen. So generally we know that in any kind of one second. So what is fine tuning? Fine tuning is a process where we are using the pre-trained model. For a pre-trained model is further trained on a smaller and task specific data set. Okay, so let me simplify. So whenever there is any LLM model, in the market, for example, the famous one is the ChatGPT, right? Or the any Llama 2 model, right? So these models are specifically trained on very huge data set. So what is the purpose of those huge data set is to and make the model so that they can understand the language, understand the pattern, right? That is the purpose of this pre-trained model. Okay, now these model are trained on huge, that's why it is called as a pre-trained model. But those models is not aware about the our own data, right? So if you take any organizational data, any institutional data, these kind of the data, LLM model is not aware because that has not been trained on, right? Or if you want, there is some specific task that model should do. Maybe that model know it, but they don't know our own data, right? So in that way, we have the pre-trained model. So any large language model, I can say it's a pre-trained model. Now I want to fine tune for my own data, right? So that my model gives the better results. So the pre-trained model, when we pre-train any model, those model weight is adjusted as per their trained data, as per already trained data. But when we fine tune, so this model is getting adjusted as per their our own particular task or on own particular data, so that it gives the good result. Okay, so when I say pre-training, pre-training initialize the model understanding of the data and its structure, right? I hope you understand the difference between the pre-training and the fine-tuning. When I say pre-training, pre-training means we will create the model understanding of our own data and structure. But when I say fine-tuning means we will adjust the weight as per our own data, as per the given data on which we are going to fine-tune this large language model. So this is overall, it is called as the LLM fine-tuning. I hope you understand the difference. Okay, now next, when I say, if I decided to fine tune any LLM model, these are the general specific steps we are carried out. Definitely there may be some addition or deletion, but these are the specific steps generally we are used to follow. First, our important task is to select the pre-trained model. So when I say pre-trained model means we have to see which specific model is good for my use case. For example, there are number of uh, models are available. So GPT is model available, GPT 3.5 model is available, Llama is available, Llama is available. So if my purpose of model to generate the code or to restructure the code or to fine tune the code, so definitely I'm going to use the code llama model, because it is already trained on one of the specific tasks that is I'm looking for, right? So we are going to use the specific model as per their our need. So first important task is to select the pre-trained model. The next is that gather the relevant data set. So it is very important, you have to have the relevant data set on which we feel to train. Now this data set, it is very important to have the labeled data set. You should not have any kind of unlabeled data set, otherwise model will not perform well, it is not giving the good result. So you should have the labeled data set, means your model should know what is the input data, what is the output data. So this is what I mean to call as the labeled data set. The third step is the pre-process the data set. Now when I say the pre-process the data set, it is not like that to take have the data and feed it. We have to do some kind of cleaning, we have to some kind of splitting, so divide the data into the train, test and validation. And that is something we are going to see what are the kind of general purpose pre-processing data pre-processing steps that we need to follow while we are doing the uh, fine tuning. There may be a little bit adjustment as per the model, that you have to refer their documentation while doing this kind of pre-processing, but these are the general steps we have to follow while doing the fine tuning of the LLM model. Next is the fine tuning. So what exactly we are doing now? We have the pre-trained model, we have the data set, we have done the pre-process of the data, now the fine tuning. So in this fine tuning, we are feeding this fine pre-processed data set to our model, so that this model will adapt the data and do the special adapt the data and do the specialized way of for that context. So it is well mature weight is there, so that it gives the good result. And next is the task specific adaptation. So for example, if I am feeding the data for summarization, so model will do the better summarization, so we have to do the task specific adaptation. Maybe we are feeding the data for NER, maybe feeding for the translation, for analysis, because we are not just sending the data as it is. After the pre-processing, we have to set up like in what purpose we are doing. Okay, so this will be the model will learn the data but also do the task specific adaptation. So what kind of data we are sending. So these are the key steps we are following. So we select the pre-trained model, gather the relevant data set, then pre-process the data set, then fine tuning and the task specific adaptation. So I hope you understood these steps. Anyways, we are going to see on Google Colab how to do this practically. Next, here is all this. Okay, now when I say the fine tuning, generally there are the two methods is available. It is called as a full fine tuning and the PEFT, that is the parameter efficient training. In full training, that is the instruction fine tuning, what happens, let's say this is the model. Okay, let's say this is the model for this setting. Okay, so we are updating all the weights of this model. We are updating all the weights of the model and we will have the new LLM model. Okay, so we know that there are many million and billion parameters are available in kind of large language model. Okay, so those parameter is nothing but the kind of weight, you know. So when we are doing full fine tuning, we are updating all those weights. Okay, but when we are doing this full fine tuning, or I can say instruction fine tuning, all these model weights create a new version. But the drawback of this full fine tuning, it requires sufficient memory. Also, it requires computation resources similar to the pre-training. So while the pre-training, whatever the memory and the computation was available, we have to have the similarly that. And we know that it is maybe difficult for any kind of organization, institute, or any individual to have same like an infrastructure, because it is a very high cost intensive. Okay, and why this is required? This is required so that it can handle the pre-processing of the gradient, optimizers, and the other component. So full fine tuning means we are updating all the weights. This is called as a full fine tuning or the instruction fine. Second way to do this fine tuning is called as a PEFT, and this is very famous, and generally most of the institution individuals are using, because it is a uh, using less resources. Okay, and that we will see in a minute how we have done this using the Google Colab, you know, with the free version of the Google Colab. So in the parameter efficient training, we are update the subset of the parameters. So let's say this is my weight. Okay, this is my model. So in LLM, we are only train the subset of the weight, not all weights we are doing. So how we can do this? Using the freezing the rest. So we are only train few parameters and we freeze the rest. So what happened? Because of that, we reduce the number of trainable parameter and we can maintain the original LLM weight as well, right? Because in the full fine tuning, there is a chance that maybe loss is getting impacted, maybe you know, because definitely we are updating the actual weight. Okay, maybe performance get degraded, but here we do not. In fact, we are maintaining the original weight as well. Okay, so we are taking the benefits of original LLM, plus we are updating the only few parameter on top of that, so we are not losing the good credibility of this LLM model. So this is called as a PEPT. Okay, now to do this PEP, there are the two generally famous techniques are available. One is the LoRa and another is the QLORA. So here I'm giving the only the brief, you know, the contextual information, but I'll make this separate video where we will go through the LoRa paper, how it does, and the QLORA. So I'll explain in detail. But in general, what is the LoRa? LoRa, suppose let's say this is the pre-trained weights of any large language model of size D. Okay, so D is the dimension of that matrix. Okay, so we are creating the another same matrix of D size, okay, and divide it into the two matrix using the concept called as a rank. Okay, using the concept called as a rank. So here we are this LoRa matrix. Okay, so this I hope you are getting this LoRa matrix that we have created is divided into the two matrices called as a matrix A and the matrix B. Okay, so that this size will be the same. So when we are doing the training, our this matrix is getting updated. Okay, this matrix is getting updated for our new data set, and at the time of inferencing, we are combining these pre-trained weights with our another trainable parameter, so that whenever we are giving user giving any input, it will have this, it has to go through this combination of this pre-trained weights plus trainable parameter, and it gives the output. So this is the one way we are doing the fine tuning. Okay, but I'll explain in another video, because otherwise it will take the it will take the time to explain each and every detail. But this is the context behind the LoRa. Okay, next. So next is the QLORA. So what is the QLORA? LoRa and the QLORA is same, but here we are applying the quantization on the top of LoRa. So therefore it is called as a quantized LoRa. Now generally we know that the base model is a 16-bit model. It is a 16-bit transformer model. Okay, on top of that we are having this optimizer of 32-bit, and these are the adapters. Again it is required the 16-bit. So this is called as a fine tuning, full fine tuning, and it is not, we are not using no adapter. in case of LoRa, what we can doing, so this is my 16-bit model, right? These are some optimizers, and on top of that we have the same, we are having one more matrix. Generally this matrix called as a adapter. These are called as a adapter. Sorry, in my previous stuff there is no adapter, but in the LoRa we are using adapter of equal size of the original matrix, but only it has the trainable parameter of the new dataset, of your own dataset, and we are combining these 16-bit our model with this the new trainable adapter, and it will give the new model, right? In the QLORA, what happened, the same thing is going, but we are reducing the 16-bit model precision to the 4-bit. Okay, now you can see here the purple mark is the paging flow. Okay, the green is something the gradient flow. So gradient is going from this, and these are the parameter updates. So we have the CPU, right? So the parameter is get updated and is getting reduced, and again we have this adapter, right? But in the QLORA, what we are doing, we are reducing the model size from 16-bit to 4-bit, so that CPU can also handle it, so that you can also use your own laptop or the desktop for this training. Okay, definitely as we are reducing the precision, there may be a some you have to there may be a chance of inaccurate or not good result, but there is a trade-off. Either you can choose the 4-bit, or the if you want to good accuracy you can go for the LoRa. So there is always a trade-off, okay, of that. Okay, so this is what the QLORA. So in the QLORA, you know, in and all I can say that it is similar to LoRa, but we are reducing the 16-bit to the 4-bit precision. In my previous video of evaluation, I have given one LinkedIn link. You can check my LinkedIn, where I have given the explanation and the advantage and the disadvantage of the QLORA. If it is not, in upcoming days I'll explain in detail. Okay, I hope you understood the difference between the LoRa and QLORA. I'll make another video to go in much more detail, but in basic, LoRa is a 16-bit. We are quantizing to 4-bit to use our CPU or to work on a faster way. Okay, okay, so these all about these QLORA things. Okay, so let's see how we can achieve this using the on the Google Colab. Okay, before going this, thanks to this is the Medium article I refer. This here is the Kaggle notebook I refer while building up this fine tuning using QLORA. So credit goes to them. Okay, so I'm not going to run, because again it will take some time to go through whole this, but I'll explain each and every cell so that at least you can understand. You can download this notebook from my GitHub. Okay, I'll share pasted this link so that you can download and play with it and do the customization as you require. Okay, so these are the some of the libraries. It's very important to install, otherwise it will not work. Okay, then these are the we are requiring some libraries. We are load the data set, then we are importing the auto casual LLM, then auto tokenizer, bits and bytes, and then Hugging Face argument parser, auto tokenizers, okay, and many things you just need. So here we are referring Hugging Face to download the Microsoft PHI model, and the Hugging Face related other tokenizers and the bits and bytes for these things. Okay, when you are doing this, it will ask you to put the Hugging Face token, okay, and then only it will work. So if please, I would suggest log into the Hugging Face website, create your own token to perform this, otherwise it will not work. Now here we are loading the data set. So in this loading data set, we are using the Neal code dialog sum test. So this data set, what this data set contains, let me explain you. It has the ID, it has a dialog. Okay, in this dialog we have person 1, person 2, and so dialog between the person 1 and person 2. Okay, here is the human summary of that dialog. Okay, and it also gives the topic. Okay, so as you can see, the hi Mr. Smith, I am Dr. Hawkins, why are you here today? So it is a discussion between the doctor, and the summary is that Mr. Smith getting checkup and Dr. Hawkins advised him to have one every year. Okay, so the topic is related to the get checkup. So these many this is the kind of data set we have. Okay, and so what we are actually trying to achieve through this fine tuning, we want to fine tune this phi model on this data set so that it can give the summary between the two individuals, okay, between the person's discussion, right? Now let's come to the second set. So here we are using bits and bytes config. Now this is very important too, because we are doing the QLORA, right? So it is, we want our model weight, should convert it into the 4-bit precision, and to convert into this 4-bit precision, this bits and byte library is very helpful. Okay, now as you can see, we are using, these are the parameters, so these load in 4-bit, so that we are compress this model weight to the 4-bit when loading into the memory. Second, to do this, to have this quantization, we use the methodology called as NF4. NF4 is the normal float distribution. So it distribute all these 4-bit across the all neural network. So it is not only so there are other many methodology how we can distribute this for normal this 4-bit weight. I'll explain in another video, so where I'll explain all this quant type. Okay, how there are different quant type available, but this is the generally very popular quant type that is called as a NF4. Now as a compute D type, we are using compute D type where we are using torch, that is PyTorch for this, and we are using float 60. Okay, and for the double quant we are making false. So what actually double quant will do, it quantize this model twice with the two different quantization function. Okay, sorry, with the okay, with the two different quantization functions. So to improve the, sometime what happens, single quantization not gives the good result, so you have to do the double quantization with different quantization technique, right, to improvise the result. So here we are making false because that is not the requirement. Okay, and these actually help us to make the QLORA. Okay, so we are using this bits byte configuration method, okay, to do the quantization, to do the QLORA. So we are quantizing the so what actually we are doing, we are quantizing the pre-trained weights of model to 4-bit and keeping the fix during the fine tuning. Okay, so this is the thing. Next we are using the model name Microsoft PHI-2. Okay, we are making device map 0, so that what actually this device map does, when we are doing this fine tuning, okay, it will only keep all the memory weights to the GPU 0. If you keep auto, so because generally what happens, any large language model, let me go to this paper so that then in detail. So as you can see, this large language model is very large in size, and maybe our GPU memory is not that much of capable to load this whole LLM into the memory. So when we say device map auto, it will divide all the large language model into the different parts. As you can see in the screen, we are dividing large language model into the 5 parts, and then we are allocating each part to each GPU VRAM, GPU 0 VRAM, GPU 1 VRAM, 2 VRAM, CPU RAM, hard drive. So we dividing LLM into the different parts and allocate each part into the specific GPUs, okay, so that this LLM can load into the memory. But in our case, what we are doing, we are only keeping the device map to 0, so that our LLM, because it is very small in size, it can load into the 0 GPU VRAM. Okay, so I hope you understood this. Then we are keeping this quantization config as a bits and byte config that we have already declared, and then we trust the remote code as a true and use authentication as a true. Once you hit, this model is getting downloaded as a checkpoint. Now this model is downloaded, right? Now it is very important to do a tokenization, right? So in the tokenizer, what we are doing, we are using our model tokenizer only. Trust remote code true, padding is left, we are adding the end of token true, add BOS token true, use fast false, and then we are, wherever there is an end of a sentence token, so tokenizer dot pad token is equal to tokenizer dot end of sentence of token. So what happened, sometimes these sentences are very small, okay, they are very less in size, okay, but when we are doing any LLM fine tuning, it is very important that all sentences of equal length. So whenever there is a small sentence, right, we have to fill up those gaps. So those fill up gaps we are filling up with the end of sentence token. Again, there is a one more thing that we are doing padding side as a left. And now you can see that when you are doing any LLM fine tuning, it is recommended to the left padding, not the right padding. Why it is so? Let me explain you here. Okay. So in any decoder only model architecture, it is very important to the left padding. For example, let's say I love Apple, then there is a pad, right? This is the input, and the output we are expecting the I love Apple pad because it delicious. Now adding this pad, it will lose the context, it will lose the next generation, okay, it will lose the connection between the two words, right? So that's why we are keeping this pad on the left side. The sentence is getting full and we have the complete semantic information is a continuous. So I love Apple because it is a delicious. That's why we are keeping the left padding and not the right padding, because if we keep the right padding, there may be chance that we are losing the semantic information. So it is recommended to keep the padding as a left during the fine tuning. I hope you understand. Okay, so we are using this tokenizer, model tokenizer to do this. Then we are mentioning this generation function. In the generation function, we are taking the model, then P max len is 100 and sample is true. So what happened here, we are passing this tokenizer this information. So specifically what happens, this function will help you to generate the output based on the input, right? Now if you look at this line, what happened actually, we are loading the while generating the output, we are using the help of GPU so that the generation will happen very fastly. And then one generation is done, again we are loaded, we are giving in the format of in the form of CPU, so that for the generation purpose, pre-processing purpose, we are using GPU, but once done we are passing to the CPU, because there might be a chance we require to use a CPU afterwards. So this way, this is the way we are doing the optimization. Okay, and then we are returning. Next point is that let's test this. We have tested this using the zero shot. So till now what we have done, just we have loaded the library, we did the bits and bytes configuration for a QLORA model, we downloaded the model, we initialized the tokenizer, we define the function of generation the output. Now after this, we wanted to test our base model, original PHI model, for some test data set, right? So here what happened, we are uh, fetching up some dialog, we consider that as a prompt, and we fetch the summary from our test data set and see how the output it look like. For that we are using the 10th sample of test data set, how it looks like. Okay, and we are feeding up to the model to check the output. Okay, now you can see the input prompt is something that there is a person who is talking about the birthday. The person one says that happy birthday, this is for you, Brian, right? I'm so happy. Then person 2 is saying, I'm so happy you remember, please come in and enjoy the party. Brian, may I have pleasure to have you dance with you? So there is a something, the party is going on, this is the conversation, right? And the what is the human summary is that uh, Brian's birthday party, and Brian thinks person 1 looks great and charming. Okay, so the person 1 attends the Brian birthday party, Brian thinks that the person 1 looks charming. So this is the human summary. What model summary of zero shot? So okay, so let me explain what is zero shot first. So zero shot means we are not giving any example to our model, we are just asking the question and model generated. Okay, so this is called as a zero shot. So in zero shot what happened, person 1 and person 2, so what the model is giving in the zero shot, sorry. So person 1, person 2 at the party, and person 1 ask if they can have a dance, person 2 agrees and compliment person 1 on their appearance, and person 1 thanks them and express their happiness with the party. So this is a long description. I know that this summary is also good, but it is not actually summary. Some okay, but human summary is very short and very easy to understand the whole discussion. Our model is not that giving the summary, but not that as what we expected. Okay, so now let's do the fine tuning. Okay, now as I mentioned, this is the something very important you have to look at. This is a pre-processing data set. Okay, so in pre-processing data set, it is very important to create the prompt first. Okay, so this is the so in the create prompt first, what we are doing, we are creating the prompt something like first introduction as a blurb. So below is the instruction that describe the task and write the response that appropriately complete the request. In the instruction key, we are giving instruct, and our instruct is that summarize the below conversation. In the response key means output we want, and the end key means the end of the discussion. So this is the something we initialize the variable blurb. In the blurb we have the introduction. In the instruction we will have this instruction what our model actually wanted to do, what our model actually do. Then input text, in the input text we are giving the dialogue. Okay, and if dialogue is present, then we are giving the dialogue. In the response, the summary of that, and the end is the end of the key. So we are formulating this our data in a such a way that so that model has the all the information, right? The instruction plus the response plus what the intro, so this way we will have the, and we are creating the list of all this. So this function is helpful to create the prompt format. Okay, after this video you can just go through line by line. If you not understand any part, let me know. Okay, so in the list we have this blurb, instruction, input text, response, and right. Once done that, we have to get the maximum length our model supports. So this is the function how we can get the maximum length of any model. You can use one so that you can see what is the maximum. Okay, why this maximum length? Because we have to create when we are feeding any instruction to the model, the length should be the maximum, otherwise model will not able to uh, create. So we have to create a data set of maximum length, and this is the function it helps to get what maximum length supported by my model. Then this is the pre-process batch. So when we are doing the fine tuning, we are convert our data into the batch, and this is the way we are doing the batch process, right? So we are creating the batch of maximum length, okay, of text, right? And we are sending, and truncation true. So what exactly truncation means? If any data beyond that maximum length, we are discarding that stuff. Okay, so we will only create the batch of maximum length. Now there are many way of and there are many logic how we can feed this data. This is one of the simple strategy to batch the data, but as per the use cases, as we are only doing with I can say kind of very simple task, but when we are doing any industrial project, there are many methodologies are there, logics are available how you can. Okay, maybe in other video I'll create on. Okay, next, this is the pre-process of the data set. So whatever function we have created, so we are doing this pre-process of data set. So in the pre-process we are sending the data set, and then we are doing the uh, yeah. So what happened here is that so in this we are formatting and tokenize so that it is ready for training, because now we have created the prompt, we have the data. Now it is very important to convert into the tokenization, right? So here for that we are using the model training, and this maximum number of token is of the maximum length, right? So this is something that we are pre-processing. We are create the data set. Okay, we are map using the create prompt format. Then after we are applying pre-processing to each batch of the dataset and remove the instruction, context, response category fields. Okay, so once the pre-processing done, okay, we are removing that part, remove this column name as well. Okay, now filter out the sample that have input id exceeding the max length. So for that we are using this line of code. Then we do the shuffling of the data set. So for that we are using shuffle seed, then return the data set. Okay, this way we are doing this part. Then after done this, we are doing this pre-processing of the data set. Till now we haven't started the fine tuning, guys. So we are doing the pre-processing of the training data set and evaluation of the data set. Once done, we can see the training size of it is 199 and the validation is 499 of 3. Okay, so we will have the feature called text, input IDs, and attention mask. Okay, and that is something is required, right? Because the tokenized data, on the tokenized data only the model can learn. Once done that, we are now preparing our model for the QLORA. So for that we are using the PEFT library, on from which we are preparing model for k-bit training. Okay, and we initializing this stuff. Okay, so prepare the model for k-bit training. So for this we are creating the original model, and we will have, so using this prepare model for k-bit method of it, we are preparing the model for QLORA. Now these are the some of the configuration it is very important to do for this fine tuning. So we are creating the rank 32 as I mentioned earlier. As you can see in my previous you know the prepare PPT, here we are setting up the rank. So on similar way we are setting up the rank. So rank as 32, LoRa alpha as a 32. So when we say LoRa alpha, so it generally it's scaling the factor for the learn weights. So whatever the weights we have learned, we are scaling up that. Okay, so that's why we are using the LoRa alpha as a 32. Then we have the target modules called as Q project, K project, V project, and dense. Okay, and these are the bias as a none, LoRa dropout 0.05. This is a conventional, but you can change as per your requirement. Then task type as a casual LM. Okay, and then we are enabling this gradient checkpoint. Okay, and this is the PEFT model. So we are, so get PEFT model. This is again one of the function in this PEFT, and we apply all this configuration to our original model to get the PEFT model. Okay, now once we will have this print number of trainable model parameter, we can see how trainable parameter is available after this PEFT. Now you can see the, I do not know how to count this, but this all model parameters very huge, and we are only training only this much of parameter. If we calculate this percentage, only 1.36 percentage out of whole parameter we are training this. Okay, so see how this PEFT is efficient. So only we are training this much of parameter of this, and then we are combining this trainable parameter with the existing model to get the output. Now just for the training purpose, okay, as I'm doing free resources, I'm only doing the 100 max steps, but you can do it, you can increase the steps as per the result. Okay, but only for the demo purpose I use 100. You can see there is not much good result, but only for you showing. You can increase if you have the good resources, you can go 1000, 2000, 3000 steps to get the good result. Okay, now this is some of the things. So here we are transformer trainer is available. We are giving model as a PEFT model, then train data set, evaluation data set, and argument is a PEFT training arguments. So sorry, so these are the PEFT training arguments we have here. So maybe in another video I'll create one more dedicated video, small video, where I'll explain the importance of each and every variable which mentioned here, so that you can adjust as per your requirement. Okay, and then these are the data collector, and then we started the training. As you can see over the period of training, okay, after each 25 steps I have mentioned here that when I'll get the evaluation, save steps after 25, evaluation steps 25. That's why after each and every 25 steps I am getting the result. Now training loss is 1.6 and the validation loss is 1.39. You can see this training loss is getting reduced in each and every steps, right? Similarly for the validation loss as well. And this way this model is getting trained. So we can see that the model and the evaluation and the training loss is getting very good result, right? Then after this now once train is that, we can see I have mentioned somewhere here where to save my checkpoint, right? So here I have given the library, sorry, path where to save this PEP dialog summary training, and I have to save here, right? So after each and everything this checkpoint is getting created. So it is very important to give the path, otherwise you will not able to use this one. Now this checkpoint 100 we are going to use at the time of inference. Okay, so close this. Okay, now you can see at the time of evaluation. Okay, okay, yeah, so here we are mentioning the original model. Okay, so as I mentioned, in the QLORA or the LoRa we are combining the original model with the another trainable model, right? So here in the we are giving original model plus the checkpoint and the other parameter, right? So other parameters, right? So each trainable we are mentioning false, because at the time of inference you should make it false. Okay, if you want to train this model again, then you can make it true. So it is mentioned as false because I want to use this model for my inference purpose. Now these are the line of code through which we want to evaluate the model. Now you can see, this is the input, this is the output, and this is the PEFT model output, right? So again, this is a person 1 and person 2. So I'm using the same, my input, that is a happy birthday wala discussion. In the baseline human summary, the human summary that we already know. Now see how the PEFT model is giving the result. Okay, we have seen in the in previously that the was this. So you've seen that the base model, that original 5 model, is giving very huge summary, right? But in the, let's say in the PEP model, how it is getting. Now Brian birthday party is success, Brian friend compliment Brian appearance as they have drink together to celebrate. I think it is more close to human summary. I'm not saying it is too accurate or too expected that what we want, but it at least better than the our original 5 model, right? It is close to human summary, but this can be improvised if you increase the number of steps and the other parameters. Okay, now to evaluate the model, as I mentioned in my evaluation of the rack system also, you can use this ROC, that is called as a recall oriented understudy for gisting evaluation. Okay, it is very famous for the summarization and translation. Okay, please watch my previous video, I explain. It is used the n-gram methodology, okay, to evaluate how this machine generated output and the human output is good. Okay, now you can see, we go, it's generating the human baseline, original model summary, and the PEP model summary. So this kind of data set we have creating to see how it is performing. And then this is the evaluate library. We are loading the rug and see the result. Okay, let me jump to this. Now you can see the original model rog is 41%, 15%, 31. Okay, now the PEP model rog is 35%, 13%, and 26%. So yeah, on the rog calculation, the output is percentage wise is not good, because original model is giving better and the PEP model. But see, again, we have train on only 100 steps. If you increase, it may give the good result, but always human evaluation gives the better. And I can see the human evaluation and our evaluation, the results are good. Okay, but definitely you can do this so that you will get the good and good rock metrics as well. So this is the mathematics way of do the evaluation, and the human way. Sorry, this is mathematical way. Okay, okay, so that's all, guys. I hope you understand these things. Okay, how to fine tune the any LLM model using QLORA. I would recommend, please download this notebooks, play with that. Okay, if you have any doubt, please comment it so that I can explain in next video. Okay, till that time, thank you and all the best.